Okay, so the title of my talk is here. This work is made in our Institute of Solid-State Physics in Chernogolovka, and I would like to introduce my collaborators, co-authors. The samples we prepare in group of Axel Lorke in Duisburg, and high-quality wafers we obtained from group of Lucia Sorba from Trieste and Pisa. Okay, my introduction will be quite short because at this conference there is no sense to speak about edge states. I only say that edge states are arising at the sample edges in the quantum Hall effect regime, and the transport in this regime can be described as transport through this one-dimensional edge state, as was first shown by Büteke. Okay, also about quantum interferometers. Now everybody here knows that with help of edge states and quantum point contacts, it's possible to realize two types of interferometers, Fabry-Perot interferometer and Mach-Zehnder interferometer. This picture is from the review of Adi-Stern. And just as a history, this great interest to the interferometer, it was arising after this work from group of Heiblum. In this group, Mach-Zehnder interferometer was realized. But as about Fabry-Perot interferometer, there is a big activity of group of Goldman, as you know, and it is very interesting that the first realization of the Fabry-Perot interferometer, it was 20 years ago by Van Wies. What I want to pay your attention, all these interferometers, as I described before, they rely on quantum point contact. In the quantum point contact, two edge states, they are counter-propagating near each other. They originate from different sample edges. They are so counter-propagating. And electron transfer is between these counter-propagating edge states. My question is it possible to realize interferometer device for co-propagating edge states? This problem is the transport between co-propagating edge states. It's something different. In this transport, we should work with edge states which are at the same sample edge. And if we transfer electron between them, we should not change the sign of the group velocity of the electron. So this is another transport problem, and there are some theoretical publications. This is the latest two ones, which calculate different transport characteristics in this situation and compare with counter-propagation. And if I want to make interferometer, what should I do? I should take sample edge. One edge state is going along the sample edge, and another edge state which should be independently contacted. It should be far away. After that, I should bring two edge states into an interaction in some small region. Also, they should be disconnected after that, and should be another region of the interaction. So, for an electron here in this edge state, it goes here, here, here. It can be transmitted between edge states here, or can be so-called reflected. Really, it goes along the edge state. And the same in this situation. Electron can be transmitted here or reflected. So there are two trajectories for one electron, this trajectory and go to the contact, or this trajectory and go to the contact. And if I change the flux quantum through the effective area, I change the phase between these trajectories, and so I will see oscillations. This is just an idea. And this is experimental realization. I start from our quasi-carbonate geometry, which we used for many years for study transport between edge states. And idea is the following. The sample is a square form. It is macroscopic sample about 1 millimeter. Also, we have macroscopic region, etched region inside. So we have outer edge, we have inner edge, and ohmic contacts are made to both edges. Also, we use gate, this is gray, to deplete two-dimensional gas under the gate to a low filling factor. For example, in quantizing magnetic field, we can obtain filling factor 2 here, for two-dimensional electron gas, and fill factor 1 here. What is mean for edge states? Under the gate, there is one edge state which goes along the sample edge. And here there should be two edge states because of fill factor 2. It means that one edge state is going along the gate edge, and here two edge states are in connection. They run together in some distance. And these edge states originate from different contacts, so they are independently contacted, and I can apply potential imbalance to these contacts, and it means that I apply potential imbalance between these two edge states, electrochemical potential imbalance between these two edge states. This region, it is of order of several microns in the real sample, so this picture is not on scale. And to make interferometer, what I need? I need to divide this interaction region onto several interaction regions with the help of small gate fingers. And you see in this picture that these gate fingers are connected to the main gate. So around one finger, I have the situation which I described before, exactly. So one edge state is still going along the edge and also under the fingers. And another edge state, which is from inner contacts, it is connected here between the fingers, also goes around the finger, and also connected here. So I use several fingers just to make some device which is analogous to the Fabry-Perot interferometer to have multiple reflections, because I can say that here it is a reflection of electron, here it can be transmitted or reflected, and so on. If I have, for example, 10 fingers, I will have multiple reflections. I want to pay your attention that it is not a real Fabry-Perot, because in my device there is no backscattering. It is not real reflection, it just goes away, and number of so-called reflections is just the number of the fingers. Of course, it should be smaller, the size should be smaller than the coherence size. So the size of one finger is about 200 nanometers. And this is also different from electronic Mach center interferometer, just because there is no etched region inside. There is no etched region inside. So if normal Fabry-Perot interferometer is a quantum dot, and Mach center have antidot inside, I have no dot and have no antidot. So it's something different. And this is experimental results. If I'm working with a sample without this gate finger structure, I can apply current between outer and inner contacts and measure voltage and change magnetic field around filling factor 2. For this experiment, I use quite a sample with moderate mobility with high concentration to have wide filling factor 2. And the signal will be along this dashed line, no special features. If I'm working with my interferometer samples, there is a shallow structure of the oscillations along this behavior. These oscillations are more pronounced at the high field edge of the plateau. They are not so pronounced at the low field edge of the plateau, and they are equidistant in the magnetic field. I can estimate period, and it is roughly correspond to our size of one finger. The same experiment can be made around filling factor 3 with the same one edge state under the gate, so really for the same edge states. And you see also oscillations. The signal a bit noisy because small signals. But in any case, we have equidistant oscillations. Okay, I demonstrate that I can see interference oscillations, but now it is a question. If I am speaking about two edge states, they originate from nearest Landau level, spin split. So what is the coherence between spin splitted edge states? The answer is the following. Energy structure in this interaction region is the following, just like Shklovsky. in contrast to a simple Butterkey picture in the real samples, Landau level is pinned to a Fermi level in some region, which is called a compressible state. The nearest level is also pinned to a Fermi level, and between them there is a gap. So incompressible quantum Hall state at a local filling factor 1, for example, here. And of course, if I want to make transport from this point to this point, I should change the spin of electron, and it will be a problem with coherence. But if I apply high enough electrochemical potential imbalance, I can obtain a situation of flat band. So I should move this part of the picture down. And electron here, it can move along the empty Landau level to this edge state. Of course, it should relax, but it can relax far from the interaction region in contact, for example, so I can forget about it. And it means that this is the answer why we see the oscillations really at high imbalances. You see these values about millivolts. This is because we should apply electrochemical potential imbalance higher than the spectral gap, Zeeman gap in this case. But after that, there is a question. If I want to study fractional quantum Hall state, so a fractional local filling factor, for example, 1/3, what should I see? And is it possible to see interference at all? Because we have lowest Landau level pinned to the Fermi level, we have electrons here, and here we have fractional quantum Hall state. I cannot really show this state in this picture because this is single particle picture. I only can say that in this region it should be gap at the Fermi level. This state is characterized by its excitation spectrum, as Laughlin excitations, and by the edge excitation modes as normal quantum Hall, fractional quantum Hall liquid. And if I apply electrochemical potential imbalance, I should take an electron, really, and to add to this fractional quantum Hall state. So I cannot say in advance, is it possible to see interference or not, because I have at the sample edge both electrons and both quasi-particles. The experimental result is a bit strange. I see interference for complicated fractional local filling factors like 4/3 and 2/3. For example, here for 4/3, I see, here you see denoted the shallow oscillations, which are absent for samples without this finger structure, and also for 2/3. This is for two different samples. I see on this signal this shallow oscillations structure. So I can say that I see interference oscillations for these fractional fillings, but for it's very strange for me. I don't see interference oscillations for the simplest Laughlin 1/3. I see only the signal and no this shallow oscillation structure. And my guess is very simple. I'm not sure that it's correct, but the idea is the following. If I have here 2/3 or 1/3, I should remember that these complicated ground states, they're constructed as a field Landau level and quasi-electron and quasi-Hall state on this background. So this field Landau level, it gives rise to the branch in the edge excitation spectrum, in the excitations. And I see interference oscillations only in this situation if I have filling Landau level as background in this fractional filling. So I can say that I see interference oscillations for normal electrons, even in the fractional quantum Hall effect regime. And for 1/3, as in this picture, where there is no field Landau level, I don't see anything. So this is conclusion. First of all, this Fabry-Perot interferometer is realized for co-propagating electrons. I can say that even at fractional fillings, I have interference conditions for normal electrons, if it's possible, of course. And about the period, I'm quite sure that I cannot obtain that my period is determined, first of all, by the effective area of the interferometer, which is sensitive to the magnetic field because of screening at the sample edge, which is sensitive to the Finan factor, to the magnetic field. And it is not so straightforward to compare periods for fractional oscillations and integer oscillations. They are different, of course, but I think that they are determined, first of all, by the effective area of the interferometer. So that's all.
I may be wrong, but I think Fabry-Perot is definitely the wrong analogy. I think a more correct one is called the Lumber-Gierke interferometer, where you have periodic scatterers, but only action in one direction. And it's sort of similar to what they do with optical fibers. They put periodic planes of scatterers, and then it becomes like a one-dimensional Bragg refraction. I mean, you said yourself that the Fabry-Perot is not your analogy. Have a look at Lumber-Gierke in the classic optics.
Yes, maybe you are right. So just it was first idea to realize as Fabry-Perot, but now I understand that it's really not Fabry-Perot. It's a different type. Yes.
Yeah, I guess you two should have a lunch discussion. Speaking of lunch, we should press on a bit. Our last speaker of this session is